Okay, so this will be analysis day 2. Real analysis day 2. And we're going to be looking at properties of the real number line. Okay. All right. So in order to get this started, just recall the distance from A to B is given by the absolute value of their difference. And this is the same as the distance from B to A. Okay? So this is just a way to geometrically interpret the distance from A to B on the real number line. So we have R, and we have A and B. This length here is given by the absolute value of A minus B, which is the same thing as the absolute value of B minus A. Okay, so again, here A and B are just real numbers. Okay. Okay, so recall a theorem from last time. And I'm going to give this one a name now to stay consistent with the book. So 219. So if A is a real number with 0 less than or equal to A, which is less than epsilon, for all epsilon greater than 0, then A is equal to 0. And the proof that we gave for that was by a contradiction. We suppose that it's not equal to 0, but then we can just divide A by 2 and we get a new smaller number. We call it epsilon. And but yeah, that was in last lecture on real analysis. So we're going to keep this in mind. We're going to look at a definition. Okay, so definition. Okay. So this definition says if, So first we can say let A be a real number and epsilon be greater than 0. Okay. So the epsilon neighborhood of A is the set. So capital V subscript epsilon of A, and this is equal to the set of all X that are real numbers such that the distance from X to A is less than epsilon. Okay, so this is the definition of the epsilon neighborhood. In upper level analysis courses and in topology courses, these are sometimes referred to as epsilon balls. Because you're not on the real line, you're in higher dimensional space, and instead of just a straight line like this, if you're in 2-dimensional space, then it's like a little ball. But just keep that in mind, that if you ever see epsilon ball, it's the same thing as epsilon neighborhood. Okay, so theorem. And this is theorem 2.2.8. Okay, from the textbook that I suggested that we use. And it says that if X is an element of the epsilon neighborhood of A for all epsilon greater than 0, then X is equal to A. So in the textbook, it doesn't read exactly like this. I just shorthanded it, and I like this better. So if X is an element of the epsilon neighborhood of A for all epsilon greater than 0, then X is equal to A. Okay, so the proof of this is actually not hard. Once you see it, you should be able to understand it. So, proof. So let's suppose the hypothesis. So suppose X is an element of the epsilon neighborhood of A for all epsilon greater than 0. So in particular, this means that this inequality holds for every epsilon. So, so this implies here, if X is in this set for every epsilon, X must satisfy this for every epsilon, right? So this implies X minus A. Now, you should note that the absolute value is always non-negative, right? So 0 is less than or equal to X minus A, which is less than epsilon, for all epsilon greater than 0, right? So if we look at theorem 219, so if we have a real number with 0 less than or equal to that number, which is less than epsilon for all epsilon greater than 0, then A is equal to 0, or whatever that quantity is there is equal to 0. So we can say by theorem 2.1.9, this quantity, whatever that is, must be equal to 0. All right, and this is equal to 0 if and only if these two quantities are equal to 0. So we can say, hence, X must be equal to A. Right? So because we can pick epsilon as small as we want, this quantity gets smaller and smaller and smaller. Eventually, like, it has to be the case that it equals 0, because we can pick epsilon for any epsilon greater than 0. Okay. So we should probably note what this looks like, right? So what an epsilon neighborhood looks like on the real number line, it helps visualize things. So if there's R, and here's A plus epsilon, there's A minus epsilon. So this is an epsilon neighborhood around A. And anything in here is in that neighborhood, right? But we can pick epsilon. So for this theorem here, if X is in the epsilon neighborhood of A for every epsilon, then we can pick like a smaller epsilon. And we can pick a smaller and smaller on either side, which means that for every epsilon, if we can do that, this theorem tells us that this quantity has to be equal to 0, which means that they're the same number. Okay, so these are important theorems to note. In particular, This is a good one to have on hand, right there. And that one is just a consequence of this one. Okay. Okay. So let's look at some more definitions. So we have an epsilon neighborhood definition, and we can use that to say something about two numbers equaling each other. Okay, so definition. All right, so let S be some non-empty subset of the real numbers. Okay, so part A. Okay, so S is bounded in above if there exists some real number U such that X is less than or equal to U for all X and S. So this is what it means to be bounded above. So part B, S is bounded below if there exists some L such that X is greater than or equal to L for all X and S. Okay, so this is what it means to be bounded from below. So in part C, S is called bounded if it is bounded above and below. Okay, so let's look at like some examples here. So suppose that this is R, and then suppose that suppose that this is my set X. Now here, this set is bounded below and above, right? There are numbers that like if you pick that number right there, that's bigger than any number in S. If you pick this number here, then that's smaller than any number in S. So this is a bounded set on the real number line. Now, this leads us to our next definition. which I'm just going to point to it. So here, this is called the nth S, or infimum of S, and this is called the sup S, which is called the supremum of S. So formally, so let's continue on with this definition. So, if S is bounded above then U is the supremum of S. This is written sup S. If so 1, U is an upper bound of S. And part 2, if V is less than U, then there exists some little s prime in capital S, so that V is less than s prime. So this is a very important notion in real analysis, and that is of the supremum of S, written sup S. And then see if I can squeeze it in here. So if S is bounded below by L, so it's bounded below, then L is the infimum of S, written nth S, if, I'll write it over here. So this is again the infimum of S. If, part 1, L is a lower bound for S, and then part 2, if V is greater than L, then there exists some little s prime in S, such that little s prime is greater than L. So this is the infimum of S. So if you look here, there's like some element right there. The infimum of this set is right here, and the supremum is right here. So note, it's important to note that the infimum and the supremum are not necessarily members of the set S. Okay, so if I do an example up here, let S be the set of all 1 over n such that n is a natural number. Okay? 1 over n such that n is a natural number. So what does this set look like? It's just 1, 1/2, 1/3, so forth and so on, right? So clearly the supremum of this set is the smallest. So the supremum is also called the smallest upper bound. So that's the supremum. So if you look at all upper bounds in this set, so for example, 10 is an upper bound on this set, but it's not the smallest. 2 is an upper bound. 1.5 is an upper bound. Among all upper bounds on this set, 1 is the smallest. So sup S here is equal to 1. Okay, so the infimum is the largest lower bound. Okay, so if we look at this set 1, 1/2, 1/3, 1/4, so forth and so on, we see that, so like -1 is a lower bound on S, okay? -0.5 is a lower bound on S. Among all possible lower bounds, 0 is the smallest. So the n of S is equal to 0. Now notice that the infimum of this set is 0, but 0 is not in that set. 0 does not exist inside that set. But it is a bound on the set, and it's the smallest possible bound. Right, so in one way that you can, like, we're not going to give a formal proof of the infimum being 0, but if you think about it, like, okay, suppose that 0 wasn't the largest, the largest lower bound on this. Suppose there was something that was like a little bit bigger, some positive number. Well, then that positive number would be squeezed inside one of, like, in between one of these elements in S, and that wouldn't work. Okay. All right, so supremum is the smallest upper bound, and infimum is the largest lower bound. Okay. All right, so here's a lemma. Okay. So it says, what does it say? Okay, so U is equal to the supremum of S if and only if the following two conditions hold. So S is less than or equal to U, or I'll use X. X is less than or equal to U for all X in S, and part 2, if V is less than U, then Oh, this I've already wrote this down. Then, yeah, so then there's some S prime and S with, so I already like, there's actually two definitions you can think of it for being the supremum, and I actually wrote down this one instead of the kind of like more classic definition, but it doesn't matter. It's the same thing. So ignore this one. It's exactly what I wrote down. Notice that U being the supremum of S if and only if and only if is a characterization of this. So it's basically a definition. So this is the same thing as saying that. So what was the one I wanted to write? So it says an upper bound U for the non-empty set S and R is the supremum of S if and only if so again, this is like another characterization of the supremum. If and only if for every epsilon greater than 0, there exists some little s of epsilon that's inside of S, such that what is it? U minus epsilon is less than little s of epsilon. Okay, so this is kind of an upper bound for U is the supremum. So an upper bound for S is the supremum if and only if there exists some element of S such that this U minus epsilon is less than that element of S. And this is for every epsilon. So it's quite a bit of almost like, there's a lot of details going on. And this is something that you're going to notice when you take real analysis, is that it's very detailed. You have to kind of stop and read through every little piece, and your logic from this course, like your logic with like if and only if statements for every there exists, that needs to be down so that when you read this, you're able to understand what it's saying. So let's look at a proof of this. So it's a biconditional statement, so we have to prove both directions. So I'm going to start off. So an upper bound U, so I'm going to say let U be an upper bound for S. Some non-empty subset in R. Okay. So I'm going to suppose first that that for every epsilon there exists this number such that this. Okay, so so let U be upper bound for S, and suppose let's use a direct proof here that for every epsilon greater than 0 there exists that with this. So all right, so for every epsilon greater than 0, there exists some element in S such that U minus epsilon is less than S epsilon. Okay. So all we're doing is supposing the hypothesis here, right? Okay. Okay. So, all right, so then all we have to do is to show that if there is an upper bound, if there is some number v that's smaller than u, then it's no longer, it's not an upper bound. So so we can say next let v be strictly less than u. And so if we go back to the definition that I just erased, right, in order to be a supremum of this set, that's what we're trying to show. We're trying to assume this and show that it's a supremum. We have to show that if this is true, then there's an element in S that's bigger than V. That's all we have to show. So next let that and set epsilon equal to u minus v. And note that this is greater than 0. Since u is greater than v, u minus v is greater than 0. Okay. All right. So this is some positive number, right? This is some positive number here. So what can we say here? So epsilon is equal to u minus v. Oh, so then, so we're going to use our hypothesis here. So note that for every epsilon greater than 0, there exists that, right? If u is bigger than v, then this is some greater than 0, and we just call that epsilon, right? So then we apply this hypothesis. So then there exists. And if you want to distinguish this epsilon from all like this up here, I could just call this epsilon naught. It's still an epsilon. So then there exists little s of epsilon naught. It's an epsilon right there. So epsilon naught, which is in our set, such that this holds, right? U minus epsilon naught is less than S of epsilon naught. But you probably don't see it, and you won't see it in the textbook. So maybe I'll write it out like this, such that, so u minus this, so u minus epsilon naught is less than S of epsilon naught. But what is epsilon naught? Epsilon naught is that, right? So it's u minus v, which is less than S of epsilon naught. Then you have u minus u, and then minus minus v, which means that v is less than epsilon, S of epsilon naught. So v, that's an element, so recall, this is not a part of the proof, but like, that S right there is an element of capital S. So that v could have not been an upper bound on the set. Hence, v is not an upper bound for S. In particular, what if we think back to what we've shown, this, by the way, this says V strictly less than S sub epsilon. So what have we shown? So if V is less than U, then there's an element of S bigger than V. That's what we've shown. And that's the definition of U being a supremum, because U is an upper bound, and if there's some number less than U, then there's a number in S that's bigger than that number. And we can say and U is equal to sup S. Okay. So that's proven one direction of this if and only if statement. Okay, so now we have to do the converse. So conversely, right? Suppose U is the supremum of S. So now we're assuming this part here, and we want to show that for every epsilon there exists some S and capital S that satisfies this inequality here. Okay. So the way I'm going to do this, suppose that, and let epsilon be greater than 0. And so this is the hypothesis, and now we're picking an epsilon, so this is for every epsilon, so we're just choosing any arbitrary epsilon greater than 0. And we want to show that there exists that with that property. Okay. All right. So, and since U minus epsilon is less than U, we're calling that this is an epsilon here, by the way. Since U minus epsilon is strictly less than U, epsilon is a positive number, right? U minus epsilon is not an upper bound for S. Because U, if we're supposing U is the supremum of S, U is the smallest upper bound, right? So if U minus epsilon is less than U, then it's not an upper bound for S. Okay. Okay. So since it's not an upper bound for S, there's something in there that's bigger than that, right? Hence, there exists some little s of epsilon within big S such that U minus epsilon is strictly less than S of epsilon. And again, that is an element of S. Okay, which shows the second part. So if U is the supremum, then for every epsilon greater than 0, there exists this element there. Done. Okay, so what I want to emphasize here with what we've done, so we've proven this lemma, we proved one theorem today, and then we proved a theorem with epsilons in the last lecture that's on YouTube. Which, by the way, my laptop had to be reset, and I lost like three videos that I was planning on uploading this past weekend. I'm using my personal laptop now, but my work laptop's out for now, and yeah, I wasn't able to upload anything. So I have to re-record all those things. But real analysis day 1 is still up on YouTube. So in that first lecture, we did 1 epsilon proof. Today we did several epsilon type proofs. The way that you're going to learn how to do this stuff is that you probably don't clearly understand it all the way through. You watch me do it, you write down with me, then you put away the video, write it out again, trying to understand each line, just memorizing it, trying to figure out what techniques happen after another, and just keep on doing this on your own, writing the proof over and over again. Like you should write this proof probably 4 times on your own, if not more, right? That's how you're going to start to pick up on how to do this. And when you're rewriting the proofs, you need to ask yourself, like, why? Like, let u be enough ground and suppose that for every bit. So why are we doing that? Well, that's the hypothesis that we assume when we're proving one direction. Why does there exist this? Well, it's because what we just assumed. Why that? Why that? Why that? At each line, ask yourself why, and try to like verify with yourself what's going on. And if you can, start like a group me, like between all of you that are working on this right now, and go back and forth with asking each other why this line, until you verify for yourself that you got it. Okay. So again, you should be reading from the textbook that I suggested, which is on, the title of it is on Blackboard, and there is a PDF online. You should be reading chapters 2, right? Chapters 2 and 3, skimming chapter 1. And then also every proof that I do on the board, write over and over and over again. Okay. Okay. I guess that'll be it. We won't have class on Thursday because of Thanksgiving. So, but I will still post a video. So just keep track of YouTube. I have a few videos that I'd like to post for you to watch. Okay.
I have a question.
Yeah.
When will our final be for the semester?
The schedule is online, and I can look it up real fast. If you just, whenever you need to know your finals, just do UHD fall 2020 final exams schedule. Let's see. So we were Tuesday, Thursday at 11. So December 15th.
Okay, thank you, Professor.
Okay, I hope all of y'all are staying healthy and safe. I know it's been a really rough semester for all of us. Just getting used to this, and I'm going to keep that in mind as I'm entering grades. I'm going to have to keep that in mind. So if you're stressing, please don't stress too much. I'm here with you. So okay, well, I will upload some more videos, and I'll see you after the break.
Thank you. Have a happy Thanksgiving.
You too.